Okay, let's start. I wanted to show you a new method of resolving RLC circuit in series. This is a very good method because for those that cannot remember equations, it's a very good method. Let's have XL, XC, the source voltage, V, the current I, or XL, XC, and the drop in every element here, VR, VL, and VC. First thing to do is to draw the vector diagram of the impedance. So let's draw it. It's R, X, L, X, C. Let's see what we have here. We have a triangle, a rectangular triangle. This is phase angle between the current and the voltage. And remember, we measure this angle from the current to the voltage. And if we are anti-clockwise, it's negative. And if it's clockwise, it's positive. Okay, so what can we write here? We can use Pythagoras theorem, which says that z squared is equal to r squared plus the difference squared. Tangent phi is equal to the difference of the rectances over r. The good thing about this method, if we multiply this vector diagram by I, we obtain voltage diagram. Voltage diagram, I will draw it here. VL, VC, and V total voltage. This is a rectangular triangle. This is VR, and because it's this diagram by I, we can write the result RI, which is VR, is L times I. This is, and XC times I is the drop in the capacitor. We can also write that V squared is equal to VR squared plus the difference squared, and tangent phi is the difference of voltages over the R. But remember that it's the same, it's this one multiplied by I, we obtain it automatically. Remember that I have to draw the current, which is common to everyone, so it's here. We see that VL is the current is lagging in the inductance, and the voltage VC is lagging the current. Okay, it's minus pi over 2. If we multiply again by I, we obtain the power vector diagram, which is what we are interested in. I have so many formulas that I can put. I can say that R times I squared here, it's also VR times I, and VR, remember VR, which is here, it's V times cosinus phi, and we can write formula that we know for active power, and this is that. Now, if I draw VL times I, which is QL, I will write it here, QL is XL times I squared or VL times I. Okay, this is the equation for this vector, power vector. This is QC, which I will write here. QC is XC times I squared. It's equal also VC times I, okay? And this one is what we call the apparent. It's Z times E squared or V times I. This is the apparent power. And we have the famous triangle. Here the difference, this difference, I will write it down. This is QL minus QC, and is equal to the difference here times I squared, or it's the difference of voltages times I. And this difference, which is here, it's V times sine phi. V times sine phi. And we obtain the famous equation for reactive power, which I'm writing here, and this is Q. Remember that Q can be positive or negative. Here phi is negative, that's why our reactive power will be negative. Okay, what can we say? It's a rectangular triangle. We can write famous equation, S squared equals B squared plus Q squared, or tangent phi is Q, or the difference QL minus QC over P, which is Q over P. Okay. Thank you. If you like it, you share it. If you don't like it, don't share it. That is life. Thank you.